between this real mass and this Fi parameter. So let me recapitulate. So real mass parameter, which I wrote as m, is associated to the background value, and theta theta bar, for global U1. Now there is also Fi parameter, which is also real, zeta, and that's related to the background value for the vector superview, which corresponds to U1J symmetry. That U1J symmetry is a symmetry whose current I wrote before. So this is also a global symmetry, but global symmetry, and which has a particular name. I wrote this U1J. So this is a topological, so-called topological U1. So there's a very nice structure. So you might begin to wonder if there is any correspondence. They look so similar. If there is any correspondence. And then the full-fledged answer to that is the 3D mirror symmetry, which is well, one example I mentioned in the last hour. But I'm going to come to. I'm going to come to that particular example, 3D and 2D mirror symmetry. So in order to see the structure more clearly, let's discuss the moduli space, vacuum moduli space, so 3D equal 2 series. And just as in for the N1 case, vacuum moduli space, well, of course, the non-trivial thing about supersymmetry theory is that there is a non-trivial moduli space of vacuum, and that's some space with a dimension. It's a continuous, and if you turn off the linear mass, everything is holomorphic. Now. So vacuum moduli space. So vacuum moduli space. I'm going to discuss the vacuum moduli space because it's one of the way to see the duality. In fact, that was the original argument to see the duality. Now, in the vacuum moduli space, it's known that there are two branches. And the reason is the following. So again, let's come back to the situation where we have vector superview for gauge symmetry. And recall that this contains the term theta theta bar. And then all other fermions over here. And then there are chiral multipliers. And now there is a kinetic term. So this is the standard kinetic term. But this is the same, as I tried to emphasize here, this is the same form as the coupling for the real mass. So in particular, if you know that, they should contain a mass term, which is this sigma squared and phi squared. Well, in fact, to some extent, they're all the same thing. But here, this is not the real mass, but this is the vacuum, dynamical thing. But nevertheless, the structure is the same. So this should be something parameter. Right. And then, so I want to discuss the vacuum modular space. So vacuum, of course, the point where the potential is minimized. And then, of course, you have to minimize this potential. And it's a square and product of absolute value squared, which means that either one of these should be 0. Well, if there are many such things, there are indices ij, etc., there is a choice of, say, let's phi 1 to be non-zero, but sigma 2 to be non-zero, etc. So there are different things. But suppose that this is the only thing. And then there's just a branch where phi is 0 and sigma is non-zero. Or the other way around, phi is 0. So phi is non-zero, sigma is 0. There are two different branches. And then this is the branch called the Coulomb branch. And this is the branch called the Higgs branch. And well, for example, it's called the Higgs branch because this phi is a scalar. So if you get which is charged under the gauge symmetry, unless it decouples completely. I assume that they are not decoupled completely, and then it's charged under gauge symmetry. So if you give a back, and that gauge symmetry is broken, so that's why it's called a peak. Now, there are two such branches. Now, the question is, what happens to these branches? How do they look like? And of course, that depends on which theory you discuss. But since I want to come back to that particular duality example I mentioned, let me discuss 3D n equal 2 SQD with non-trivial. So this means, as I said, 1 hour ago, is the and there is a charge 1 plus 1 and charge minus 1 Q and 2 kilograms. So this is a theory. Or maybe I should okay, so phi 1. Yeah, let's take this. And then, so what's this? First of all, what's the Higgs branch? And in the Higgs branch, this, well, I changed the notation. Maybe I need to. Anyway, this Q is the same as this phi. So in the Higgs branch, that's non-zero. So these are the non-zero. So apparently, there are two complex parameters. But the point is that these are charged under gauge symmetry. They are charged the plus 1 and minus 1. So the non-trivial stuff, so in the Higgs branch, we have this gauge invariant combination, which is Q tilde Q. Well, recall that everything is a variable, so I don't really worry about the order. So this is the method, which parameterizes the Higgs branch. And so this is just some complex number. And as I will see, there is going to be some points. Right, so I mean, I said that these are the two branches, but of course they intersect at the point where everything is zero. When everything is zero, this branch and the Coulomb branch and the Higgs branch make contact. There is a point contact. And I try to represent it by here. So this is the point where right, so there is no scale, so this is the conformal point. So this is the cone, and this is the conformal point. So the Higgs branch is easy. Now, what about the Coulomb branch? And the Coulomb branch is indeed more difficult for multiple reasons.
Excuse me, why is it conformal?
Well, it's the point where everything is zero.
The QE decoupling, there's still a dimension for coupling.
Yeah, that's right. So, okay, so, right. So okay. So when I say that, I implicitly assume that I already go to IR. Well, sure. So sure. Why not just write that the sigma equals 0, phi equals 0. So that's the point where that's the intersection of Coulomb and the Higgs branch. Which is the point. Maybe I should. So what's the Coulomb branch? Whatever Coulomb branch it is, it should intersect it.
So what you meant to say is that infrared of that theory is not gapped as opposed to the rest of it. On the cone, if you flow to infrared, the theory is gapped.
Right. Right. So let's go to the Coulomb branch. And then I have to come back to this U and J. In fact, I haven't said too much about what this U and J is. And then that's the problem because, I mean, for example, right, so the only thing I said so far is that this is related to the current is given by epsilon mu sigma. So this is the only thing I said so far. So what's the symmetry? What's the symmetry? Now, it's related to this duality, in fact, for rays. That's why I think that. So that's more or less, I'm coming to the duality slowly. So in 3 dimensions, again, there is a special property of the 3 dimensions. There is a gauge cube. So this is the 1 form, and then there is a 2 form. And then you can dualize. scalar such that star f equals, or this is equal to star dA equal to d phi. So this is the dualization. In fact, if you go back to 4 dimensions, maybe I should mention 4 dimensions for pedagogy. So in 4 dimensions, we have this A, for example, and this A, if this is a 2 point. So if you dualize, if you take a Hodge dual, there is something called FD. It's the Hodge star in 4 dimensions of dA. And then this one is the derivative of some field known as AD. And this is the 1 form. And this is the 1 form. So in 4 dimensions, if you take a dual, and the 1 form is mapped to a 1 form. And thus phi is electromagnetic duality, for example, of the electromagnetism. Well, it's called it electromagnetic duality. There is an electromagnetic duality in the Maxwell equation, for example, if you include the monopoles. That's why Dirac was excited about it. And that statement is very specific to 4 dimensions. And this is essentially the 3D, well, not essentially, it really is the 3D counterpart of that statement. And you can discuss a little bit more explicitly. In fact, this is a good exercise. In fact, so let's start with this U1 gauge theory, abelian gauge theory, and say let's forget about all this Fermi of the zero. Let's take a gauge theory, and it's U1, so F mu nu. And then the exercises show that you can dualize this. Well, I could almost give you an answer. Maybe I don't have time. So maybe I could state the answer exercise. So I could dualize this to be G squared. And then, so this is G goes to 1 over G. This can be written as du phi, where phi is related to the f by dualization. And besides, this phi has some periodicity properties, which goes like phi plus G squared, periodic scalar. So this is another Lagrangian. And this is a rather useful exercise. I mean, the idea is roughly, the idea is that this is F mu nu, and the important point is this is not just a fundamental field, but it's a derivative of the gauge field. But you can impose the constraint, by introducing this Lagrange multiplier. This term. And then now you can regard this F mu nu as a fundamental field. And then probably I could write this phi even. And then you integrate out this F mu nu. And after that you obtain this term. And you can keep track of this factor G such that this becomes 1. G goes to 1. So for abelian theories, you can explicitly dualize, and the end result is that gauge field is dualized to this periodic scalar. And there is a shift symmetry also.
What's going on with the indices there?
Sorry?
This derivative on phi.
Sorry?
The constraint, phi.
Phi goes to
Upstairs.
Upstairs, the constraint. There's a derivative on
Phi.
derivative of phi.
Because of the contraction.
Yeah. Oh, yeah. That's right. Yeah, that's right. Sorry. Yeah. Well, I mean, yeah, that's right. But although that itself, right. So anyway. Yeah, that's right. Yeah, that's right. So probably I should have written this as a phi.
Yeah, you want, that's right. You
Yeah, that's right.
derivative of that.
Yeah, that's right. Right. So this is following. Thank you. Right. So I wanted to impose the Bianchi identity. So I could do this partial integration and obtain this term. And then get rid of the F mu nu to obtain the term. Now this is a very useful exercise. In fact, it shows very clearly that this is the dualization, at least in the most typical abelian case. And you can essentially use more or less the same argument if you are clever, and then you can show the S duality for abelian for the N-equal 2 series. That's what we did in the 90s. Or, for example, there is a derivation of the mirror symmetry for from 2D 2, 2 series. And in fact, at least the first half of the argument is just repeating that argument for N equals 2D series, but with supersymmetry is manifest. So instead of integrate out some bosonic fields, we integrate a superfield. And that is more or less, well, part of the, almost half of the derivation of the Miller symmetry by Fourier back, for example. So you can use this argument in various different cases. Now,
so it's much more generic than n equals 2 story.
Yeah.
It's just particle vortex.
yeah, that's right, exactly. Right, so it's a particle vortex, or there's some other people might say boson vortex duality. Right, so I mean, right, so I'm not an expert, but people in, say, quantum Hall or insulator, conductor, transition, superconductor, transition, etc., people use this duality. So if you, right, so I had a condensed matter current. Oh, okay, maybe I'm decreasing that. But anyway, so, right, so, oh, okay, so maybe I shouldn't have eliminated that, but, right, so what does the Coulomb do? And the reason I talked about is that there is a natural variable which emerged in this process. So that's this dual. This is called this one is called the dual photon. Well, because it's a dual photon. Now, and then, well, of course, the subtle thing is that this is periodic. So this itself has some ambiguity. However, there is a natural. You can cook up some natural operator. Monopole operator. Where B goes like, well, this means semi-classically, 1 over G squared, and then there is phi. And then I should have I, because so this is a natural variable.
Only one sigma.
Yeah, that's right. Yes, that's right. So I'm coming to that. Yes, that's right. And right. So as he said, the modular space is scalar. So I want holomorphic quantization. And for that purpose, I take this sigma. Recall that this is a subcomponent. Yes. So this is a natural object monopole operator. And the claim is that this monopole operator. So right. So I sort of digressed a little bit. Not digressed, but I tried to explain the Coulomb branch. And in the Coulomb branch, there's U1J symmetry, which is represented by action of this phi. And that's the monopole operator. So the conclusion is that. So let me recapitulate. The Higgs branch, Higgs branch capital is parameterized by this M. So that's awesome. And the Coulomb branch is V, which goes like exponential, as I said. So this is phi plus sigma. And in particular, you can. This is like a cylinder. So this is periodic in phi directions. So this is like a cylinder. Where there is a symmetry here, phi. This is the phi direction, this is the sigma direction. And the symmetry is a U1J. Whereas in the Higgs branch was a cone. And then there is a symmetry. This is the U1. There is a U1 symmetry, which is a Freiberg symmetry. So there is a Freiberg U1 actual Freiberg symmetry, which rotates is the same thing. So that's a Freiberg symmetry. So this is a gauge symmetry, but there is also a Freiberg symmetry. Let's call it axial symmetry. And then if you do this axial rotation, this thing rotates. Because M is rotated by a phase. Now, if you look at this, there is obviously a contradiction. Because I said that I want to keep in with this. We'd like to combine these two. Except that this symmetry acts only on this monopole operator, but not here, for example. So whenever you make a contact, it doesn't make sense if there is a finite size circle. Because that's where this U1J acts. But U1J should not act on the Higgs branch where there is a contact. So there is a clear discrepancy. And in fact, there is a way out. And it's known that there is a quantum correction to the Coulomb branch, which you can compute in a Abelian case with the one-loop computation. And then there is a quantum correction. There is a quantum correction which pinches off the cylinder at a certain point. But a certain point is precisely the value sigma equals to phi equals to 0, which is the point where these things intersect. Well, metrically it's not really like that, so there is a smooth, it's like a cigar, so probably I should write it in this way. So you can compute the metric two-prong branch. And then you can fit in the Higgs branch there. And this is how the vacuum modular space of this SQED with boundary looks like. So this is the vacuum modular space. Now, well, this is a very suggestive one. So maybe I should also emphasize that this takes approaches to no, it's not right. So, but anyway, metric rate. So, sorry, no, this is right. So, anyway, right. So this is like, and then this is impressive because you find that there could be some threefold symmetry, rotate different branches. They look like this cone or cigar. And from this point, three cigars emanate different directions. And in fact, the answer is that if you go to a different description, they are the same. So let's keep in mind that this is SQED with NF equals to 1. But there's a different way of reproducing the same looking modular space. And that's this XYZ model. So this is the XYZ model, which I defined at the beginning of this lecture. And in the XYZ model is a sort of very simple series. There is no gauge group whatsoever. And the only thing is that there are these chiral multiplets whose superpotential is XYZ. Of course, it's easy to identify the modular space, vacuum modular space for this guy, because as known very well in supersymmetry, the vacuum modular space is this is a 0, and all the same for all x, y, and z. So this is the branch where explicit writing x, y equal y, z equal z, x equal to 0. Now, and then there are three branches obviously. So x we did non-zero, y equal to 0, z equal to 0, or there are permutations. There are three permutations. And in this case,
in that cylinder pictures,
yes.
It seems to suggest there's a symmetry along the sigma directions, but that is not apparent from the vertex operator of monopole.
Yeah, okay, so in fact that's a good point. I'm coming to that. So in fact, this expression, so there are quantum corrections. So this expression, there was a, this was, I didn't write as an inequality, and the reason is that there are quantum corrections. So in fact, that's a good question, so let me understand. So in fact, I said that this is parameterized as V. So what happened to this V, in fact? And the statement is after quantum corrections, this is split into two parts, V plus and V minus, two variables, V plus and V minus. Where in this asymptotically, V plus goes like exponential in this notation, phi. Right, so let's call it, say, for example, let's see, phi, I don't know, let's see, phi half for simplicity. And then there could be phi up in this region, and V minus goes like exponential minus phi up. Asymptotically, it goes like that. So the statement is that, right, so originally you have just this, and that parameterizes everything. But there are quantum corrections which pinches off, and correspondingly, that's split into two parameters. It's parameters different branches. And then they have different, the sign in front is different. And in particular, that means, for example, under the U1J, these are charge plus 1, but these are charge minus 1. Right, so the structure is that we have M, B plus, B minus, which parameterizes three branches. And it's very similar here. So we have again three branches. Maybe I can't write too much here. There are three branches. And the three branches, obviously, well, I didn't write too much too carefully. But obviously the branch is x non-zero, y non-zero, z non-zero. So there are three branches. So you can can identify, of course there is a symmetry x by z, but you can identify x to m to be x, and then b plus to y, b minus to z, for example. So this is the identification. Well, of course, I didn't really justify that these are really the same. I just suggested that there are three possibilities, partly because of time constraint. But I could provide a little bit more evidence, in fact.
Masahito, what happens at higher loops to this picture?
Okay, so I think I think the computation is one loop exact, I guess. I mean, the metric, for example, that's it. For the at least for the Abelian case, that's safe. Right. Yeah, if you're interested, that's described in the paper by Hori and Holtz, for example. Right. So, right. So, and this duality is described. Well, that's right. So this particular duality is discussed in the classic paper by Haroni, Saiberg, Intrivigator, Hanani. Sorry, I missed a single person, but we should keep this off record. But anyway, okay. But anyway, but anyway, so all these brilliant field theorists in the 90s. So right, so that's actually a very good paper because it contains some review material, which is very readable. So I strongly recommend that paper in '97. So we could try to provide a little bit more. Right, so evidence by thinking about the symmetries. Well, of course, the global symmetries of these two should be the same, B plus, B minus. And there is a meson, which is the gating part of operator. So the gate symmetry is plus 1, minus 1, minus 1. And these are 0. Now, there is a U1 axial symmetry, which I alluded somewhere. Maybe I will delete that. Right. So there was actually U1 symmetry. So this is a Fourier symmetry, which goes like a plus 1, plus 1. And also there is a topological U1 symmetry, which is associated with the shift of the dual photon. And it's a shift of the dual photon, so these are fundamental is not here. And as I said here, there's a phi and minus phi, so the signs are different. So that means that there are the symmetries, they are charged on the plus 1, minus 1. Oh, let me take this one. Actually, for later purposes, let me take this minus. That's just what it is. And then since this m was QQ tilde, this is minus 3. Now, right. And then
why monopole has no U1 charge?
Sorry, which one? So
B plus, B minus.
sorry, this is a meson.
B plus and B minus.
No U1 gate charge. Sorry.
I thought they were monopole.
Yeah, it's a shift of the dual photon. Right. So. Right. So it's a shift of the dual photon. So right. So this is a gate symmetry. But that gate symmetry, if you do that, even if you do the gate transform, you know what? Maybe I could say that. So F star is D phi, for example. So if you do the gauge transformation, F stays the same, so phi is the same. And then in fact, if you do carefully, actually it turns out that there is plus 1 here. And that's related with this parity anomaly stuff, which I don't have time to explain. But let me relate it to parity anomaly. So I'm not going to explain this because the time is ending. But
you have 5 extra minutes, right?
Sorry?
You have 5 to 10.
Yeah, sure. That's right. So let me So this is the charge assignment for one thing, for one of the series, and then well, of course there is a similar charge assignment for this series, and this series is really trivial. But the gauge symmetry is not, as I've been trying to say, is not very fundamental, so you can forget that. And you should have the same charges. But there is a symmetry. U1, well, let's see, we use the same name, U1J, for example. And since the superpotential is x, y, z, as long as the sum of the charge is 0, it has a symmetry. So since x is identified with m, so I could try y, z, and this to be minus